to LAC. I imagine. Can you go here? I can. Hello. So welcome back. I assume you're all caffeinated and alive and awake. So we start this section, the new session with Shanxian Li and Thomas Mackenzie, and they will be presenting spatial room impulse response extrapolation using the image source method.
Hi everyone, Hi everyone, I'm Zhen Xian. I'm currently a PhD student at INSA Liang. So hope everyone enjoy the campus and the canteen in the INSA. This work is a collaboration with Thomas Mackenzie from the University of Edinburgh. I will have a quick introduction to talking about what is the VR spatial audio and what's the spatial room impulse response. So imagine you are playing a VR game, like the one I put here is the Half-Life Alyx. Like you want to hear some people walking around you, like you hear the enemy from the back of you, and when you're walking in the space, you want to make sure the subject is continuous changing. So that will bring you the realism and the interaction in the game. In order to do this, we have the room impulse response. Many people may be very familiar from this idea. So if if I'm standing in this room and you are listening me here, the sound will transfer from my mouth to your ear directly, and some other sounds will jumping on the wall reflection to your ear. So if we put a microphone at the listener position, we will get a recording like this. We give the impulse to the room with like a clip or the bloom. We will say there is the first peak for the direction sound. Then the early reflection and the reverb part. If we if we replace this mono microphone to the spatial microphone, we will get the spatial room impulse response. That's except the time arrival of the reflection. It also brings the information about the direction. That's the high order amsonic room impulse response we will use in the VR game or VR concert. But in order to have the full room in the VR, in acoustic, we need to do a lot of measurement. Imagine you have 10 different positions for the source and 10 different positions for the receiver. So you will need to do 100 times the measurement. Like the picture showing here, this will be a super heavy job. So let's come to our method. Like in order to save other people, save everyone from the heavy job, we found like this spatial room impulse response extrapolation using image source method, which require only one measurement and the room geometry. So let's check in the impulse response from the room. So here is the testing room for us. You can see we have 3 different positions of the speaker and 7 different positions of the receiver. We choose the 2 different pair, like a super different pair. The source 1 to receiver 1 and the source 1 to receiver 5. These 2 like 2 different corners of this room. It should sound pretty different. And we checking, actually the impulse response for these 2 only have the different at the beginning part. At the very early part of the time, if we looking the full impulse response, it's have pretty similar. So we got the idea like in the same room, the impulse response are like have two different parts. One is the silented component, and one is the diffusion component. We assume the diffusion component is the same at the room, but yeah, it's only works for the normal room, not like the room super long or like a room have the L shape or different kind of shape. So in this method, we're only working with the silent component. That will saving a lot of the calculation complexity. We use this method called GSVD. So in this way, we can separate impulse response into two parts. The silent component part, which is the direction and the early reflection. Then another is the diffusion component. Then we can have the image source model for the arriving time and the direction. So image source model is a simulation way to show the reflection of each wall. Imagine every reflection on the wall, it's also can represented by a virtual source at another side of the wall. So we're taking the two reflections at each wall. So we got like a lot of the virtual source, and we move the virtual source, we can get the simulation of the reflection. After we got the virtual source, we can get the arriving time of this reflection, the direction of this reflection, also the amplified, which relate to the distance of the source. After we got this, we can manipulate the arrive. So basically, like we will cutting this arrive, cutting this out, then shift it on the time, scale it, rotation it to like you have the sound from the front. You cut this, then move it, like adjust the amplifier depend on the distance. Then rotate the angle, so you will got a new source, looks like, sounds like from the new direction. And we got the result. After we got the spatial room audio, we render it to binaural audio, so you can hear through the headphone. If you want, there is a QR code you can scan with your phone, then listen with the headphone. I will play it through the speaker here, but I'm not sure what it will sound like.
Only the direct sound without any acoustics.
This is the origin sound before the rotation.
Only the direct sound without any acoustics.
This is the generated sound with our method.
Only the direct sound without any acoustics.
This is the target. So we hope these two sound similar in this end. I think this speaker cannot tell the direction of this video, but if you listen with the headphone, it sounds pretty good.
Only the direct sound without any acoustics. Only the direct sound without any acoustics.
Sorry, I don't know.
Only
Okay. Then we come to the evaluation. First, a quick repair for this data set. Like we will measurement a room like this. We have the different kind of the reflection on the wall, and for different position of the source and the listener. We will testing on the. We want to move the sound from the S2 source 2 receiver 4 to the S3 receiver 2. So from the blue one to the red one. So if we're checking the result we got at the time domain, we can see the main ticks match perfectly, exactly the directed time, like it's at the red box. It's it's matching so perfectly. It's much better than we thought at the beginning. And some early reflection match the pair, but some others not so great. But in all the loudness or the RMS, it's basically matter we only have the 0.2 dB of the whole impulse response. If we then at the frequency domain, the part like over 1K hertz, it's matched perfectly. It's less than 1 dB difference in the higher frequency part. At the lower frequency part, it have some different, but compared with the origin thing, yeah, it's show some matching. This may be because of the we use the ray tracing. We use the image source method, which is the geometry acoustic. Like for the high frequency waveform, it's performs much better than the low frequency. Then the important part is the direction of the arrival. This we're checking like on the red part over here. Like this is the origin sound, and this is the target sound. You can see the middle one is the generate. The main point, the big black point in the middle, it's shows the direction sound. It's matched pretty perfectly. It's come from the same direction, same amplitude, and the same diffusion. And for the main reflection angle at here, like the angle is pretty close. Like yeah, it's matching the same we want to be here. The only problem we got here is at the backward, at the sound from the back of the height. We got the target measurement showed like you should feel the wall behind you, but our method cannot reproduce this part. This problem is mainly caused because when we isolate the arrival, we only cut it on the time domain. But actually, if you have two arrive at the almost same time, you cut this one, you maybe also cut a little bit signal from another arrive. So this will cannot show the direction at the back of your head like this. So for the summary of this finding, our method have the good works good on the direction sound, for the timing, the delay, the direction, and the amplitude. But for the early reflection, it's partly accurate. It shows something. It looks, it sounds great, but it's not matching so perfectly. And for the perception, coloration, and the RMS level, it's matched pretty good, especially at the high frequency part. The main source of the error comes from the two part. Firstly, we can check in the room of the room we do the measurement. It's not ideally a shoebox, like you have all this small stuff on the ceiling, and this thing like hard to modeling in this method. And when we measurement the geometry distance of the wall of the various speaker, you will got a little bit error in it. And after, if you got a reflection on the wall for 3 times, the error will keep adding on it. So that's in the time the arriving time is not matching so correct. And another question is the speaker we use in the measurement is only to the one direction, and for the speaker, like if you hear at the different position, the frequency will be a little bit different, and that will cause some colorate in the final result. So for the future, first we want to add in some image source message collaboration to, we have the recording signal, we have the measurement data from the room geometry. We want to match these two data, then like adjust a little bit to make it combine much better. And another way is we want to use the beamforming array. Like if we use the beamform, like if we have two different arrival of the reflection coming at the same time but different direction, we can separate into two parts, then rotation it. It will help us to reduce the error. Thank you. All the code and audio is uploaded on the GitHub. You can find it with this link or this QR code. Okay. Thank you, everyone.
Questions from the audience? Okay.
Hi, thank you on your presentation. I have actually several questions. So first, it's regarding your limitations on room shape. Like, is it because you developed your own image source model and then you like are bound to shoebox?
I think like we own how to say that? Like the beginning point is like we want to find a very easy way, very easy to calculate way. Like because only the like first field reflection and the direction is the matters for the perception. Another part is not so much different for human hearing, and for the geometry, is like this image source method is how to say that it's a pretty well-known method. So I didn't I do the MATLAB coding by myself, but the method is already there. For why we only ask for the normal room, because if you stay in a super long room, like the reverb from the different wall, you will hear the different. Like if the room is super long at this direction, and you can hear the reverb at the front is different than other direction. So even without the reflection peaks, if you remove the reflection, you only check in the reverb part, it's still different. You can perception the difference. So this why this method only limited to the normal room.
Yeah, I mean, okay, so, but there are like, you could maybe take some of the existing like image source model algorithms or engines available, and then you wouldn't be like restricted to basic room shapes. You could then do, I don't know, yeah, just maybe as an idea, because it's terribly like difficult to make all the algebra there to make it work for different shapes. It's not easy task, and also the optimization. Then later for I don't know how many reflections are you considering, like as an early reflection.
May I checking the question again? I'm not sure I get the. So you mean the like a big shape, but not just a shoebox.
Yeah. So
it should work. It should work if you just because we just like testing this method to see is this work. So shoebox is easier on this, but yeah, it's definitely can use on the other different species. Just not the like the tube thing. It should work.
Okay.
Yeah.
And just maybe a comment or a question. Did you make listening evaluations? Because like evaluating just from the graph, like frequency or stuff, it's not like...
We didn't do the listening test for this method now because we want to add in another thing onto it. So it's maybe comes from like maybe next month or next month.
Okay.
Yeah.
Thank you.
We will do that.
Thank you.
Any more questions from the audience? Yes.
I was just wondering if you've considered using the classic stereo microphone, where you have a pair of microphones that are at 90 degrees to each other, so you can get some directional information from that.
Sorry, I didn't hear from the microphone.
I'm wondering if you've considered the option of using a classic stereo microphone, which has two cells that are at 90 degrees to each other, so you get some directional information from that straight away.
But we use we use the spatial audio, and here we already get the direction information. Yeah.
So you're getting the direction from the
from
ambisonics
from the Amazonic. Yeah.
So anyone else? Oh, sorry.
Just like to add something to that question. The usual stereo reproduction is not easily to understand. It's quite psychoacoustically. But there were research some years ago that you can model it with ambisonics, but you did a full
modeling.
You did a full sound field analysis and not just that stereo reproduction. But that stereo reproduction in itself is not well understood. There are still some psychoacoustical effects in it which are difficult to get at from a research viewpoint. So I think that would be a complication to add that not really well theoretically, not really well understood reproduction. You have an easier approach if you use a full sound field, which you can capture with mathematical tools. I think that's a bit of an additional answer to why it's not so a good idea to concentrate on that stereo reproduction or a surround.
It's.
I want to support your.
The impulse response we got is in the spatial format, so you can play it with the binaural headphone or with the great. It's because so far we render it to the binaural because it's easy for the lacing test or something like this. Yeah, it's definitely works on it. Thanks for your advice.
Also adding to the last two comments, the advantage of the stereo microphone would be it goes up to high frequency. So the cilia is, I think, limited to 3 or 4 kilohertz because of the spatial aliasing of the microphone array.
Yeah.
So it's a bit tricky because you have basically I think they claim it's third order, but it's not for the full spectrum. It's just third order, starting from a certain frequency up to 3 or 4K. And this coincident setup would be actually maybe a bit better because it works in a higher frequency range, in a larger frequency range, from low frequencies to high.
It's the main different what we like the direction of this speaker. The difference is mainly at the high frequency part, right? I'm not very good.
No, the problem with the spherical microphone arrays is that you get spatial aliasing at high frequencies. So I think they have 19 capsules on a sphere of 8 centimeters
19,
or something like this.
Yeah.
I'm not sure about the exact values, but more or less. And that means for high frequencies above 4K, basically you cannot do this spherical harmonic decomposition correctly. And that maybe explains why your curves at the high frequencies are all online, right? You have you showed some curves, and I'm not sure if I understood it correctly, but you see at low frequencies you have a difference, at high frequencies it's all the same.
We during this measurement we have two different we use two different the microphones, the EM32 and the Zelia the M1. The result showed pretty same, like
Yeah,
we
but it's
didn't
the
see
same type of microphone. It's,
yeah.
two spherical
Yeah,
microphones with almost the same
almost
radius,
same,
so
mm.
they are pretty compatible, basically, in this sense.
Yeah,
But the coincident microphone would be maybe had an advantage that you can get to higher frequencies, just as a comment.
yeah, that's very good. May I ask, like, do you have some advice, like how we like fix this part, like how we testing is the matching is really from our method or from the microphone?
Well, you could use another type of microphone, like a tetramic, octamic. So there's microphones where you have the capsules, basically, you don't have this spherical body, but you have microphone capsules that are basically very close to one point. And that means you don't run into spatial aliasing at a certain frequency point.
Okay, I get.
So they might give you a smoother result over the whole frequency range, which maybe helps.
Okay. Thank you.
Yeah, you would have less spatial resolution, but higher frequency. Trade-offs, always.
So just one technical question. So when you recorded audio, which file format did you use? Is there a standard spatial file format for storing sounds?
Sonic B format, I think. I forgot the...
So does it also store the coordinates of the microphone?
Yeah.
Oh, exactly. Okay.
But I think this M1 microphone, like they have their own coding way, like they have their special way to transform it from the A format to B format. So I'm not sure how they actually work, but I will use in this method, I use the B format Sonic into it.
Okay, thanks.
So thank you very much, and we'll go to the next talk now.
Thank you.
Yeah. So our next speaker is Fons Adriansen, who will be talking about tape simulation. Test.
Test. Okay. Okay, this is about a technology which by now is almost 100 years old. So one question, is there anyone here who has ever worked in a studio using analog audio tape? Okay, more than I expected. Thanks. So before everything went digital, music was produced using analog tape recorders. And the whole technology was developed in the years just before the Second World War in Germany. And later the Americans took the machines to the United States, and that it was further developed mainly by the Ampex Corporation. So by the 1980s, 24-track machines were more or less standard in music studios. They were not perfect at all. You had noise, you had distortion, you had flutters. But these imperfections, some people say, provide something magical which is called tape sound. So there is probably a market for software emulation of whatever this tape sound is supposed to be. Oops, sorry. Oh, wait, I should not touch this thing. So, basic introduction to tape machines. You have a tape which is moving from left to right. The red thing here. There are three, what they call recording heads. One is used to erase a tape, the second to record the signal, and the third one to playback. So such a head is just, oops, just a magnetic, sorry. So you have a metal core with a coil around it, and at one end there's a very small gap, which is a few micrometers wide, and that's where the head is in contact with the tape. So if you send a current to the coil, you get a magnetic field concentrated at the gap, and that will be transferred to the tape. For playback, if there is any magnetic signal on the tape, that will generate a voltage in the coil. So in the overall, you have an input signal, goes to some amplifiers, an EQ, that goes to the record head, and some high frequency signal is added. We'll see later why. And on the playback end, you have the playback amplifier and EQ. So this is a bit simplified because professional machines had a lot of other modes of working. For example, you could also play back using the record head. This was necessary if you are adding tracks, for example, because they should be in sync. Also, when you are replacing part of a track with a new take, punch in, punch out, which means you had to sequence the activation of the arrays and the record heads, also switch the output from playback to input and so on at the right moment. So this is really simplified, but okay, it doesn't matter for what we are discussing. So these machines, they required a lot of attention. You needed to align them frequently, and alignment means you had lots of adjustments, small potentiometers which you adjusted with a screwdriver. And on most machines you had at least 7 of those for each track, which means for the 24-track machine, you had 168 things to adjust. You needed to do that each time you started using a new batch of tape, for example, and also at least once a week. So with a bit of experience, you could do that in 1 hour. And also there was no single correct alignment, so you could actually tune the performance. You could make a trade-off between maximum level signal-to-noise ratio, better frequency response, and so on and so on. So my original project was to make a physical model in software of this whole process, the recording and playback process, and present all these tuning parameters to the end user. So you could do the equivalent of the sound engineer adjusting his machine for the best sound or whatever he wanted. This proved to be much too complicated to do in real time, even on a modern PC, even for 1 channel. So I had the choice, either fake the adjustments, which I didn't like. So in the end, the process or the process that I designed does not have all these tuning parameters. It just emulates one particular setting of the machine. Oops. So why is this so complicated? So we need to look at some physics of magnetic materials. The problem is that if you take most ferromagnetic materials, you put them in a magnetic field, they will magnetize. And if you take away the magnetic field, they will still be magnetic. So that's an effect called hysteresis. And it's illustrated by the picture here. If you start at A, so horizontally we have a magnetic field, and vertically we have how magnetized the material will be. You start at A at 0, you go to B, then it will saturate because you can only be so much magnetic and not more. But then if you decrease the magnetic field to 0, it will still be magnetized. We are at point C here. And to completely remove the magnetizing, you need to apply a negative field, so a field in the opposite direction. And this of course, is what makes recording possible. Without this remnants, what it's called, so there would be no memory of what is recorded. But at the same time, this thing is so highly nonlinear that it's almost impossible to use it for anything analog. It's perfect for digital. Yeah? If you want to record digital data, you apply a positive field, and then you remove it, and the material will remain at point C. If you want to record the other bit value, you apply a negative magnetic field, and you end up at the negative of C. So that's perfect. But to use this for an analog signal, we need some way to make it linear. So this is an illustration of what happens. Imagine a fragment of the tape, say one sample of tape, passing from left to right by the recording head. So that's what you see here on the x-axis. Actually, the range is from 1/10 of a millimeter before the recording head to 1/10 of a millimeter after it. So the magnetic, and you say we send a DC signal to the recording head. So the magnetic field, which is sensed by that small piece of tape, increases as it passes towards the head. It will be maximum there. And then it decreases. And the signal which remains on the tape is shown below in the red curves. So it will be magnetized. Then when the magnetic field decreases, the magnetization decreases, but it doesn't go away completely. And what you get is the series of red lines below. So this is clearly very nonlinear. And the way to fix this is what we have seen before. It's adding this high frequency signal to the signal that has to be recorded. That's called bias. It's high frequency bias. So this is the result without the bias. So the input signal, which you send to the record head, and the magnetic signal, which remains on the tape. It's very nonlinear. You see in the middle we have this almost flat section, and at either end it will tend to saturate. Now, if we add this bias, things change. So here what we see is the bias signal and no signal itself, no audio signal. So what we have is just this high frequency bias. Then the magnetic field looks like the green curve, and what happens on the tape will look like the red curve. So it will converge to a value, which in this case is 0. And that's actually also what happens at the erase head. Because here I started at 0 for the red curve, but if I had started at a different value, it would still end at 0, because only every peak which is higher than the previous one erases the effect of everything that comes before it. So what you see on the left is the green curve on the horizontal axis and the red curve on the vertical one, starting at point 0 here, so the middle of the green and red traces. So it starts at high value, and then you get a lot of more or less concentric cycles which converge to 0. Now, if we add some signal, so the same bias high frequency signal, and we add 0.5, so half of the bias amplitude of DC, then we get this situation. And here, this also converges, but in this case not to 0. and we can increase the signal to 1. So this is actually what happens every time the tape passes by the recording head. So as long as we have low frequency signals, we could pre-compute the relation between the signal value and the final value of the magnetic signal on the tape. It's a 1-to-1 relation for low frequency signals. And then we could use that in a software emulation to make a physical model of this. The problem is that at high frequencies, this doesn't work anymore. So at low frequencies, we could pre-compute one of these curves, which is for different bias levels. And you can see they are all three quite linear, at least part of them. So the best one here would be the blue one, which is for a medium bias level. If you use less, then you get, for example, the green one, which has a smaller linear range. And if you use more bias, you get the red one, which does not provide more signal. Yes, it doesn't go higher than the blue one. It just requires more input. It requires more signal to the recording head. So the ideal bias here would be the blue curve. Now, if your signal is not constant during the time that the tape is passing by the recording head, then it gets much more complicated. And you can still simulate this, of course. And that's what I've done here. For example, we have a 4 kilohertz signal plus a bias. So the blue trace is the signal, green is signal plus bias, and below the red one is the magnetic signal on tape, and the only thing that matters is again the value at the end when it converges. Same for 8 kilohertz. The problem with this is that if you want to emulate this in software, you have to compute the complete history, the complete red trace from the point 0, in the middle, to where it converges to some fixed value. Now, this is, if the bias signal, for example, is 100 kilohertz, which is typical, and in a digital system, you would need a sample frequency of something like 1 megahertz to do this correctly. That means you need a few hundred evaluations of this nonlinear function, which is quite complicated. It's not just nonlinear, it has this hysteresis. So that's quite expensive. I tried to do this. I actually did this because that's how these curves were computed. And even optimized quite a lot. This was 15 times slower than real time on a 4 gigahertz PC for one channel. So it's impossible to use that in practice. You need some compromise. So what happens at high frequencies becomes quite complicated. What you see here is the relation between signal amplitude and the amplitude of the magnetic signal on tape for different frequencies. For low frequencies, 1 kilohertz, the top curve, blue, and 2 kilohertz, it's almost perfectly linear. So minus 20 dB input gives you minus 20 dB output, 0 dB input gives you 0 dB output. And above 0 dB, it tends to saturate, so to compress. But if you look at the higher frequencies, even at low amplitudes, they are attenuated quite a lot. For example, the bottom one, which is 15 kilohertz, is it's about 27 dB below. So we will need to equalize that. And what you can see also is that the higher frequencies will saturate at a much lower level than the medium and low frequencies. And that means that on playback, we need to boost the high frequencies, which is not de-emphasis, pre-emphasis, de-emphasis, like, for example, on FM radio. We need to boost on playback, which means we are boosting noise as well. So it's not really an ideal situation. So what did I do at the end, since the codec's complete process is much too complicated? I made something which consists of a set of filters and some nonlinear operations, which emulates these curves as closely as possible, and then hope that this is actually usable. And that's actually what all tape simulation plugins do. None of them actually uses the correct, complete, much too complex process. Oops. Yeah, okay, yeah, I can cover this. So if I can emulate this, then I still need to equalize it for the flat frequency response and combine it with some other things which are standardized or were standardized on tape recorders. So if we want a tape recorded on one machine to be playable on another machine, we need to standardize some things, not only the tape format and the speed and the track layout and so on, but also the actual relation between the magnetic signal on the tape and the output signal. And there were different standards in use in Europe and in the United States. But they all had this common thing that they, on playback, they needed to boost the high frequencies. So what was actually standardized is not the EQ, which implemented in the machine. It was the relation between the magnetic signal and the output. Because that is what you need in order to ensure that you can play a tape on any machine and the signal will be correct. So the actual equalizer would be quite different. It should also compensate, for example, for the response of the playback head. And then the EQ to be used on input when recording would be whatever what is required to make the end-to-end response flat. So these were the standard playback EQs used mostly from the 80s. So we had IEC in Europe, and they're dependent actually on the tape speed. So what they do is they scale the filter linearly with tape speed. So what matters actually is the wavelength on the tape, not the frequency. So that would match the tape response quite well in all cases. The American NAB one, which is the black trace in this case, was the same for the two tape speeds that were used professionally. And there was also one defined by the AES to be used at the higher speed, 30 inches per second. The NAB one also had low frequency, below 50 Hertz boost on recording and the corresponding roll-off on playback. So that had the effect that, for example, if we recorded the bass or drums, bass drum, at high level, they would get extra saturated and compressed because you had this low frequency boost. Okay, so more or less at the end here. No, sorry. So, how does it look in software now? So we had this nonlinear process which defines the magnetization, which has this frequency, high frequency loss, so we need to compensate that with an inverse filter. so we compensate the frequency response of the decoding process for low-level signals. And for high-level signals, okay, we get this compression. And then we need to combine that with the standard playback EQ and the inverse of the standard playback EQ when on the input side. So that is actually the block diagram of the application which I wrote. It's a collection of a lot of filters. Some depend on the tape speed you select, some depend on the EQ standard. And then one nonlinear process which sits in between these filters. Okay, that's more or less it. So we could discuss, if not, if it all makes sense. Yes. In the end, I produce something which actually works. Okay, it compresses and it gives you some high frequency loss at the lowest tape speed, and then you can add some noise to it, which sounds realistic to me. But okay, do we really need this, or this is just hype? My answer to that goes in its hype direction, but okay, opinions may differ. Can you do the same effect with much less complexity? I'm very sure you can. What do you get in the end? It's some level of frequency-dependent compression and limiting. It doesn't have to match what a real tape recorder does to get the benefits, if there is any. The effect is there anyway. So what's the point of using a very complex process to do something what should be simple? I leave this open, so if you have any opinions on that or questions, just ask. And yeah, the meters, they are protected. You cannot destroy them by having high-level signals. That's it for...
Questions?
Not yet, but this will be published probably in a few days, so you can make it on then. At the moment, it's a jack application, but the usual suspects will probably convert that into an LV2 plugin.
I suppose, yeah, part of the magic is also the wow and flutter effect of the tape. Have you done any research in that direction?
Professional machines didn't have any wow, low frequency speed changes to speak of, and if they had any, they were considered defect. Flutter, which is really high frequency dropouts due to errors due to non-perfect tape, mechanically, dirt on the tape and on the heads and so on. It's not a nice effect. Nobody wanted that. So what's the point in emulating it? About the noise we could discuss. Some people say a bit of noise is nice, which is why I included it actually in this processor.
Hi. Yeah. So you mentioned there's a nonlinear block in your model that you used. Is that a hand tweaked block, or have you looked into like nonlinear system identification to like record a sample from an actual machine and optimize it in a way that it gets closer to the original?
It's hand selected, let's say, but it's based on actually something similar to this one, yes.
Okay.
Because that's what you get at a low frequency end.
Okay. Come back. Too many questions. Too many questions.
I've recorded on tape. I seem to remember that there was a lot of special sauce around tape brands. Ampex 456 was a rock and roll tape. There was another Ampex tape that was more of a clean tape. So were these differences in the response curves versus the kind of ideal? And then how did that correspond to differences in the output?
Oh, in quite a complex way. Yeah. Since the complete emulation of that sort of effect was way too complicated, you can't do it here, but the effect would be that you would need different, for each type of tape, you would need different bias levels. So that's when doing the recording alignment, the bias was the first thing you needed to adjust. There were different methods to do that. And the usual method to do that was you record a 10 kilohertz signal, start the bias at 0, increase it until the output signal is maximum, then increase it again until the output drops by 1 or 2 dB. That 1 or 2 dB would be different for each tape type. And the difference you get in the end is the difference in high frequency response, mainly for each tape. So that was the second and third thing you needed to adjust. After the bias, you would tune the equalizers for the best frequency response.
Couple of unrelated questions. The first one is that going to be GPL or
yes, of course.
Okay, yeah. And the second is to do with the complexity of the first model you showed that was running really slow. Mm-hmm. So what was the main reason for that? Is just too many operations?
Well, the main
and would is the problem parallelizable?
No, that is the real problem. You can't. What you need to do is, so you have this, the green signal, which is what you send to the recording head. The red one here is what remains on the tape. And you have to go through this whole process from the middle, where the signal level is maximum, because anything before doesn't matter. So you have to start at 0 here in this curve, and go to all these cycles of the signal plus bias until it converges. And if you look at that with the practical tapes, with the normal tape speeds and head dimensions and so on, that would mean several hundred evaluations of this nonlinear thing. Not only nonlinear, it has also hysteresis. Several hundred evaluations for each output sample. And an output sample at a sample rate of 1 mega, at least, to make it more or less correct. So you get a complexity which is sample rate 1 mega times 300,000 quite complex operations per second for one channel. It's just too much. So the actual process which is now used is very simple, actually. It's all the processing is done at 96 kilohertz, irrespective of your input and output sample rate. And okay, it just takes 1% of CPU or less. So, but it's a fake. Yes, it's not a physical model, which is what I wanted to do. But okay, wasn't possible.
First of all, full marks for investigating in such depth. Having been a victim, I regard myself, of tape machines right the way back to the 1960s, and the standards there were just unbelievably poor. And I've been in the position of testing machines, and on some of them, with the old mu metal type replay heads, you could actually watch the HF response degrading as the tape was playing, just on one plate. Every single tape, sometimes even just halfway through the tape, you had to realign the damn things.
Yes.
Yeah. So getting any kind of sort of assessment of what sort of responses you get is largely a guessing game.
Yeah, but of course in a professional setting, this alignment was done quite frequently.
I think. One more.
But, and that's a remark I really want to make, nobody, no sound engineer at that time
There's two pending.
would align his
You saw
machine
that, right?
for the effect, to have a warm, softly compressed sound, as it is called today.
We have time.
They would align them for absolute best quality. So this whole idea of tape sound has something magical that came much later. And actually it did not come from the professional side of the audio engineering. It came from the high fidelity world, and where you have all sorts of beliefs. I was actually a sound engineer when the whole world changes from analog, from tape to digital. So something I've experienced many, many times is first time when musicians hear a recording of themselves done on a digital machine. And they all liked it quite a lot. They liked the fidelity, they liked the quality of it. Nobody wanted tape at that time. That came much later. And as I said, it came from the high fidelity world, really. So that's why one reason I would say, okay, this is a lot of hype.
Okay, I've heard that you use nonlinear processing for tape for the hysteresis simulation. So is this DSP oversample internally?
Which one do you mean? The one I used for the simulations?
Yeah.
That was done, if I remember correctly, so these curves, for example, they were computed at 5 MHz sample rate.
Okay, and the DSP in the JAG application?
In the application, it's 96 always. So it's
okay.
Signal is resampled to 96. Probably in the release, that will be 192.
Okay, so 4 times oversampling, do you think is enough for this application?
For what I do, yes.
Okay.
Because I don't model the bias signal directly. I just model its effects. So then something which is a lot higher than the audio range should be enough. The problem is with this nonlinear thing, you get intermodulation products. So if you have a strong signal which is near 20 kilohertz and you use the minimal sample rate, 48, you get aliasing frequencies. And to reduce that, it's better to use a much higher sample rate. Also, the whole application is really a collection of quite a lot of equalizers, of filters, which have been hand-tuned manually to do the right thing. And to do that again and again for each sample rate, I didn't want to do that. So everything is done on 96 and probably in the future 192 kilohertz, regardless of what your actual sample rate is externally.
Okay.
So we're running out of time, but the Lord of the conference has said, I can do this. But we still have a little bit of time, so one last question.
Fons, you explained how it's not feasible to do complete physical emulation. I was wondering, not for the sake of creating a sound, but for the sake of getting a feel of how to tune a tape. With all that you learn now in your physical modeling, would it be possible to compromise on the bias emulation, which you say is very complex, but could you give me something that has all these 7 adjustment points so that future generations of digital techs can learn how to like put a virtual alignment tape in, give me an oscilloscope output and tell me, okay, now you tweak this to that, tweak this to that. Because the problem is I do own several tape machines. I'm not myself qualified to maintain them.
Yeah.
And all the geezers that can do that, they're getting old and this knowledge is lost.
True.
So the question is, would it be feasible to create a virtual tape op training thing with little digital trim pots and shit, so you really can go through the motions?
Yes. So actually, are you asking me to fake it?
Fake the computationally hard part, because I wouldn't be interested in having the same bias effects, but having the same like tuning parameters. See what gets out of alignments. Look exactly on the scope. What is a shifted azimuth? What is you know, to under bias, over bias? How does it look like? Like make people like a training tool more than a sound emulator.
Yeah, that would certainly be possible. The problem there would be to make that realistic, because it depends a lot on tape type, tape thickness, speed, everything. So to get that data today, I wouldn't know where to find it really, to make it really realistic. But to make something that reacts in the same way, yes, certainly that would be possible. We could do that.
Okay, thank you, Fons.
Thank you, Nando, for sharing the session. So, a couple of information. So for lunch, we're having lunch boxes. Some of you registered for lunch, some didn't. We're not going to verify who did or who did not, so we trust you, okay? There is a limited number of boxes according to the number of people who got the lunch option, so don't take someone else's lunch, okay? There might be some spares actually, so maybe like just stick around. Like if you didn't get it, like stick around. Maybe we'll have one for you. You know, like anyway. But like first, you let the people who got the lunch option to get their lunch. Okay. There are 2. So the boxes are going to be outside of the theater. Okay.